Continuing on in section 6.4 here, there's a take note on page 383 that has a bunch of properties here for rational exponents. They have multiplying powers with the same base, which means as long as our base is the same, here they're both a's, we can add our exponents. Power to a power means we're going to multiply our exponents together and keep our base. Power of a product means we can take our exponent to each item inside our parentheses, each part of the product there. Negative exponents, we get rid of a negative in our exponent by taking it from the numerator to the denominator, or the denominator to the numerator, and making it positive. Dividing powers with the same base means we're going to subtract our exponents. And quotient to a power is just like power to a power there. We are going to take that exponent to each piece in there and then multiply if need be. So we can use exponential form to combine radicals that have different indices, or if our index numbers are different, as long as they have the same base or radicands. So if we look at example 4 here, I have an x and an x for my radicands. It doesn't matter that my exponents are different. That's fine, okay? I just need that radicand to be the same. So in my numerator, I keep my base. My exponent's already raised, so remember that goes in my numerator, and my index is my denominator. Here, my radicand is my base again. My exponent is already raised, it's higher, so we keep that as our numerator, and we get the denominator as our index. Here I'm dividing powers that have the same base, both x's, so I can use my properties, and I can subtract. I'm also going to reduce here. 2 over 8 is the same as 1 over 4. And I can subtract my exponents. This gives me x to the 2 over 4, or x to the 1/2. And since I started with radicals over here, I'm going to end with a radical. My base becomes my radicand again. My numerator becomes my exponent, and my base becomes my index, which here we don't need that 2 because it is a square root. So we get the square root of x. So even though at first glance we can't put these together because of the different indices there, we still can because they have the same radicand, and we can use our properties of exponents. In example 5 here, we're going to simplify these numbers using rational exponents. So what is each number in simplest form? The very first thing I'm going to do here is I'm going to get rid of the negative exponent by moving it to the denominator. Then 2.5, guys, means I'm going to have 2 times 16 to the 0.5, or half. I'm going to have 2 full groups of 16s and 1 left to the half power. If we wanted to, we could write that 2.5 as 5 over 2, which is 2 remainder 1. 2 full groups and 1 remainder. I can take the square root of 16. My denominator becomes my index. I know the square root of 16 is 4. So 16 squared, 256, times 4 is 1024. So I get 1 over 1024. Same idea here for b. I'm going to take the 5th root of negative 32 to the 4th power. And up here we could have done this as well. We could have simplified it and had the square root of 16 to the 5th power. The square root of 16 is 4. 4 to the 5th power also gets me here. So whether we reduced it right away and took out the full sets or did it all in one, it didn't matter. So here I'm going to do this first by taking the radical. I know the 5th root of 32, of negative 32, is going to be negative 2. I know it's going to be negative because it's a 5th root and my number is negative. So I'm going to take negative 2. 1, 2, 3, 4, 5 of them. I need groups of 5, so that's perfect. Now to the 4th power. Negative 2 to the 4th power gives me 16. So again here, I could have taken negative 32 and taken it to the 4th power first, but that's going to give me a really big number that I'm going to have to try and break down. So if I can break it down to smaller pieces to start with, that's going to be helpful. Just like we did up here on this second part, where I took the square root of 16 first and got 4, and then took it to the 5th power to get my 1 over 1024. Or here we could have broken it down into pieces, but at no point did I take it 16 to the 5th power, which we could have done. It's just going to be harder to break it down that way. So my recommendation is to break them down into smaller pieces before we take them to the power, if we can. If it's something that doesn't break down into things that are going to be good to work with, then use that exponent if needed. Feel free to pause here and give these a try first if you'd like. First thing I'm going to do is get rid of that negative exponent. I'm going to move it to the denominator. This is going to give me 32 to the positive 3/5 power. So again, to get rid of my negative, I take it to the opposite part of my fraction and make it positive. Now, this is really telling me that I have the 5th root of 32 to the 3rd power. And again, we could put that 3 inside with our 32. It doesn't matter where we put it there. Our denominator becomes our index. Our numerator becomes our exponent. Now, I know the 5th root of 32 is 2 because we've been doing a lot of these problems, and I remember that. But if you didn't, break it down into its pieces. I'm looking for groups of 5. Here I have 5 2's and nothing else, so that's perfect. The 5th root of 32 is 2. Now I can take it to the 3rd power, and I get 1 over 8. Again, we could have taken 32 cubed first and then broken it down, but that's going to be a lot bigger numbers to work with there. 16 to the 3/4 power, I'm going to take 16. My denominator becomes my index. My numerator becomes my exponent. The 4th root of 16, so we're looking for groups of 4. I have a group of 4 2's, so the 4th root of 16 is just 2. Now, don't forget to cube that, and we get 8. Oops. 9 to the negative 3/4, negative 3.5, sorry. I can do 1 over 9 to the 3.5. That's 1 over, and that was again to get rid of the negative. We move it to the denominator. 9 to the 7 over 2. 3.5 is 35 over 10. 1 decimal place, 1 0. I can take a 5 out of each of those, 7 over 2. So 1 over the square root of 9 to the 7th power. The square root of 9 is 3. 3 to the 7th power is going to be 2187. And again, we could have taken 9 cubed there. We also could have taken here 3 groups of 9's out and had the square root of 9 left. That would have worked as well. So however you want to break these down works. Here I don't have the same radicands, so I can't combine, or same indexes, so I can't combine those. But what I do have is the same radicands. So here I can rewrite this in rational form. My base is my radicand, my numerator is my exponent, and my denominator is my index. Times, again, my radicand becomes my base, my exponent becomes my numerator, and my denominator comes from my index. Since we have the same base here, and we're multiplying powers with the same base, which means we can add our exponents. This here is going to give me 3 to the 3/4. This is 2/4 right here. Common denominator there, 3/4. So I'm going to take the 4th root of 3 cubed. And I can't make any full groups here of 4 things, so I'm just going to leave it as the 4th root of 27. I don't know what happened there. There we go. Because I can't reduce that any further, I'm going to go ahead and leave it as a radical there, but I am going to get rid of that exponent and actually take 3 cubed to get the 27. Again, if we look here, we have different indices, so we can't combine those, at least at first glance, in radical form. But what we can do is, since we have the same radicands, that would give us the same base in exponential form, and we can use those properties of rational exponents from page 383. So I take my radicand to be my base, my numerator comes from my exponent, and my denominator comes from my index. Divided by, radicand becomes my base, exponent becomes my numerator because it's already raised higher, so it stays raised higher in my fraction, and my denominator comes from my index. Now, I can subtract. Dividing powers with the same base, since these are both x's, means I can subtract my exponents. I get x to the 3/2 minus 2/3. Common denominator here is 6. So I multiplied by 2 to go from 3 to 6, so I multiply by 2 to get 4. Multiplied by 3 to get to 6, so I multiply by 3 and get 9 over 6. This is going to give me x to the 5 over 6. And we don't want to leave it in a fractional exponent as a rational exponent there. We want to put it back in a radical since we started with radicals. So my index number comes from my denominator, and my numerator, since it's raised higher, is what I raise my radicand to. It's my exponent. So I have the 6th root of x to the 5th power. Same idea here. It doesn't look like we can combine them because my indices are different, but my radicands are the same. So when I switch these to rational form, which means fractional exponents here, my index is a 2, my exponent is a 1. So exponent over index. Same idea here. Exponent is 1, index is 3. I can add those. I keep my base, add my exponents, and I get 5 over 6. 6th root of 7 raised to the 5th power. Numerator, denominator, exponent, index. Denominator, index, okay? Now I'm actually going to take 7 to the 5th power because 7 is prime, so all I have here are 5 7s, but I need groups of 6 things. And I'm going to get the 6th root of 16,807. And I'm going to stop this here and continue on with another video.